Law of inertia. So yeah, so the three laws, my pet names for them are this will help you remember because you need to remember them in order, right? They're not just three arbitrary laws, they have a specific order. And so we want to, they're so important that we need to know. So first law is the law of inertia, which I just referred to as inertia. Second law is the force law. You can say it a couple ways. Net force equals mass times acceleration, or net force equals time rate of change of momentum. Linear momentum, we'll talk about what momentum is and how it's related. But a poetic name for force is cause, as first cause, second cause, first force, second force. So I refer to it as cause. The third law is the law of action and reaction. For every action, there's an equal and opposite reaction. Of course, that has, some people say, metaphysical implication. That is also how some philosophers and Eastern persons describe the law of karma. And so I refer to the third law as the law of karma, implying the equal and opposite thing. So it's a really nice way to kind of think of the laws. Inertia, cause, karma. That's a nice ring to it. The law of inertia, for every an object will stay at rest or in motion in a straight line unless acted on by an external net force. The law, the second law, the force law, cause. For every action, there's an equal and opposed reaction. So I'm sorry, that's the third law. For the net force on an object is equal to the net external force on an object is equal to the mass of the object times acceleration, or the net external force is equal to the time rate of change of momentum. And karma, for every action, there's an equal and opposed reaction. But let's focus on inertia. So I can't remember, did anyone define for me, did we get to the point of defining what inertia is? David, what is inertia? Is David there? Well, go for it, Daniel. You're there. You're about to say something. Go for
Is it me?
Yes, you. I said David. Yeah, David. You're just talking.
Oh, okay. Inertia in a sense is like all objects tend to remain in constant motion unless a force is acted on it, something like that.
Well, that is the law of inertia. That's right. But I'm asking you, what is inertia itself?
Inertia.
Hey, go ahead, David.
Inertia. Where is that? Inertia itself is like, no, I think it's like the object don't want to move. It doesn't want to move unless you have like really force on it. You act force upon it, then. So I think inertia is like I don't know how to put it, but it's like.
Well, actually, Jesus, if you look at the chat there, Jesus is on the right track. I like the word resist. And no, sure, right? It doesn't really have anything to do with potential energy, but resist is a nice word. And their dami also resistance to the reluctance of a body to move and stop and move or stop it. Yeah, I would change the term reluctance to resistance, but meaning the same thing. So yeah, you both got it. In fact, specifically, you can say that that inertia is resistance to change in motion. Resistance, yes, I do. Resistance to an object that affects its flight. Yeah, so I think the two key words in understanding inertia is resistance to change. So resistance and change. It's not resisting motion, it's resisting the change in motion. And there's a difference, right? Motion refers to velocity if you want to quantify the word, but but change in velocity implies essentially acceleration. And that's the important key, because that leads to the second law and makes the connection of the first law with the second law. So it's resistance to change in motion is what we'll use as the definition for inertia.
So,
Yes,
so,
Daniel.
so are you saying like under inertia there is a motion?
I'm saying that on the inertia there's a motion.
Yeah.
Is that a question?
Yeah, because like you said, inertia is the resistance of motion, but not the resist. You say it's the resistance of motion, but not motion itself.
So that's not what I said. What I said was inertia is resistance to change in motion.
Yeah, change in motion.
Those aren't the same things. I just said that.
Okay.
Motion and change in motion are not the same things.
So okay, so under inertia there is a motion. Is that what you're saying? Because you said inertia is the resistance to change in motion. So like if there is inertia like there should be a motion then.
So my short answer to your question is no, that's not what I'm saying. And I'm being kind of picky here because actually it is true that there is a specific distance, but the way that you're asking that question, and this is for everybody in the class, points out the subtle difficulty, or I don't want to say difficulty, but the subtle implication of the first law, which is something that you have to distinguish. So let me try to repeat your question to make sure I understand it.
Right.
In fact, could you repeat the point that you just made? Because I want to use the same language.
Okay.
Go ahead.
Okay. Since you said inertia is the resistance to change in motion, so I'm saying under inertia, so there is a motion, so there is motion in inertia, but like inertia, you said is the resistance to change in motion.
So I'm hearing you saying, are you saying there is motion in inertia? Is that what you just said?
Yeah.
Okay, so no. Inertia is not about motion or inertia is not associated with motion or the lack of motion. Let me say that again. Inertia is not associated with motion. Inertia is not associated with the lack of motion. Inertia is associated with change in motion. Do you get the difference?
Uh, actually, okay, let me just give you my understanding of motion. Like my understanding of motion is something moving like from point A to point B, right?
Yes.
Good. Then if inertia, you said is the resistance of change in motion, like meaning the change in motion maybe from point A to point B. You said that's the definition of inertia, the resistance of change, in motion. So there should be motion.
How? How are you getting that?
It's not. Because
Who knows? Oh, sorry, who said it's not?
David.
Oh, your brother all in the same room. Okay, got it. you guys you're tripping me out with that. So yeah. So, but David, can you explain to your brother why it's different since you seem to understand it?
Yeah, I think it is not motion itself, but the change of motion. That's what it is. Because the motion can be from point A to B, but in the way there might be a change from C to B. There might be a route. So I don't think it is like it is a motion, but there could be a tweak in it. So it's like change in emotion. I think it's like change in emotion and emotion again, like two. So you could have like a change in the motion itself, but not the actual motion, the first one you are thinking about. That's how I'm looking at it.
Okay, I think you may understand. You're kind of confusing me with the way because you're using motion in two different ways. But so coming back to Daniel, so you had said something right before David um, chimed in. What was the last thing you said, Daniel? Do you remember? Daniel, are you there?
Yeah. Okay. Yeah. I was saying, like, since inertia is the resistance to change in motion, so meaning there is a motion in inertia, but like inertia is just like, the change in it, the change in the motion itself.
So what do you mean by the change in motion itself?
Meaning, like, if the motion is going from point A to B, then inertia will be like the resistance from C to D. Then there is a motion already in inertia, like, because you added this change, meaning is a change in the motion, meaning there is a motion originally in inertia.
So I'm not getting what the C to D is. Like, how is it resisting C to D if it's going from A to B? If an object is going from, like, what is the other, you know what I mean? Like, what does that have to do with another space or change in displacement? I'm not getting that.
So,
So
like,
let me go ahead. Go ahead.
since you said inertia is the resistance to change in motion.
Yeah.
Yeah, so meaning it is resisting the change from A to B, right? That's the meaning, huh?
No. Okay, I
Oh,
think I got what you're saying. That's why you're calling it motion. Because what you just said from A
yeah.
to B is not motion. A to B, or the difference is displacement.
Oh, yeah.
A to, yeah. So that's just displacement.
Yeah.
The velocity is the displacement divided by time. I
Yeah.
think I get it now. So you're equating motion with displacement, and it's not. So yeah, if something is moving along at a constant velocity, right, the velocity is not changing, but the position is changing.
Okay.
So it's not resistance to position inertia, it's resistance to velocity. It's a difference. So let me give this analogy. Let's go to a different analogy. Let's say that you have a car moving down a straight on a road, and the road is a straight road, and the car is moving at a constant speed, 40 miles an hour. So you just have a car moving down a highway at 40 miles per hour, just like see my hand moving toward the camera. Okay, let me ask you this. Is the velocity changing
Yes.
in that scenario?
Yeah.
If a car is moving down in a straight line at 40 meters per second, my question to you is the velocity changing?
No.
Okay, no, it's not. Did someone say yes initially? Who said that? Who said yes? Okay, all right, so everybody agrees, no. Let's say that I have a car that's moving in an exact circle and it's also going at 40 miles per hour, well, 40 meters per second. So it's going at a constant speed, 40 meters per second in a circle. Is the velocity changing?
I say no.
Okay, Daniel says no. Everyone in the class has to speak in. You can put your hands up or thumb or whatever. So how many people say the velocity is changing? Or you said no? What'd you say? No, Daniel? So how
Yeah.
many people say no? The velocity is not changing for a car moving at a constant. That's all right. Shura. Okay. Anybody else? David. DJ, what do you say? Dami. Okay. Didier, David Edwards, Roy, Abdul, chime in. David, or David already said, yeah. Jesus, car moving at 40. Okay. All right. Velocity is a vector. Oh, I see. So, oh, David said no. I see you wrote it. I didn't see it. And so yeah. So most people said yes. I think David, and maybe a couple other persons. I wasn't looking at the writing. Said no. Abdul says no. So velocity is a vector. It has magnitude and direction. In order for a vector to change, a vector can change in two ways. The magnitude of the vector can change, or the direction of the vector can change, or both. Both the magnitude and the direction can change. In this case, the speed is constant, 40 meters per second, but the object is going in a circle. So because it's going in a circle,
Changing.
its direction is always changing. So it's still part of the vector, the direction portion. So that velocity is changing, even if the speed is constant. Okay? So when something, either the velocity, so we're talking about motion here. The first law is not just talking about any vector, it's talking about the vector of velocity. That's what motion is referring to, not speed. The motion in the definition of the first law, or in the statement of the first law, is referring to velocity. That's what Isaac Newton meant, which is a vector. So anytime the velocity of an object is changing, whether that is changing because the magnitude is changing, or whether it's changing because the velocity is changing, or whether it's the direction is changing, or whether it's changing because it being velocity is changing because both the magnitude and the direction are changing. In any of those circumstances, that is considered a change in velocity, and there is acceleration. Acceleration exists in that object during the time in which its velocity is changing. So you can see that velocity and a change in velocity are two different things. Velocity is, as we define, displacement divided by time. A change in velocity is actually an acceleration. It means the object is accelerating. It has an acceleration. And an object that is accelerating is not dictated by the first law, but rather dictated by the second law. So right now, and there's two ways, basically two ways in which the two types of scenarios kinematically in which the first law applies. It always applies to the scenario in which the velocity is not changing. So right now, my velocity is 0. So my velocity can't change because it's 0. That's one scenario, that an object is not moving at all relative to a reference point. So that is where the law of inertia applies. Another scenario in which the law of inertia applies, in which an object is moving at a constant velocity, not a constant speed, a constant velocity, meaning that its magnitude is constant, not changing, and its direction is constant, not changing. So a car moving along a straight line with a constant speed is essentially moving along at a constant velocity. And in that case, the law of inertia applies. Again, an object at rest or in motion, having a velocity in a straight line. I just forgot the law now. What is it? Oh my gosh, whatever. Oh yeah, an object will remain, I forgot the term remain, at rest or in motion in a straight line unless acted upon by a net external force. So it implies that right now I'm sitting and I'm not moving. I don't have a velocity. It means that the net force on me is 0. That doesn't mean that there are no forces, that there are forces, but all those forces combine to be have a net force of 0. And on me right now, there's basically two forces. There's there is my weight, which is acting down, and there is a force of contact with the chair, which we call a normal force, which is acting straight up. If I were to determine the magnitude of those forces, add them together, then my total force would be 0. If I'm moving along a highway in a car at a straight line at 40 meters per second, or 40 miles per hour, whatever, then I would have 2 forces acting, well, actually 4 forces. In fact, let's diagram that scenario. Diagram both of them. So a mass on the ground, like me, like I was just sitting. We'll come back to inertia in a minute. Let me just take this on. So I have a mass M. It is on the ground. It has 2 forces on it. One is the weight of the object. Force, oh gosh, really? Okay. That's not so cool. Just a second. This is water soluble. Two forces, mg down, and a normal force which acts up actually. So if I were to apply an axis and kind of evaluate those forces, that's the terminology that I use, evaluate Newton's law, first law associated with this problem. Sorry, I just filled up my ink. Probably put too much in. So along the positive x direction, I have N. So if I were to evaluate this, it would look something like this. So net force on this system, have a normal force up. I have a weight down. And so I'll make an opposite sign associated with that. And right now, the motion of the object is 0. It has no acceleration. So I know that these 2 forces will sum to 0. Net force equals 0. Basically, it's a net force. So actually, let's do it like this. I'll probably start by realizing that I'm applying the first law because there is no acceleration. So the net force equals 0 because the net external force, there is no net external force, meaning it's 0. Otherwise, I would have a change in motion. Clearly, the object's just sitting there, the motion is not changing. So that's how I know that the first law applies. You always have to evaluate the motion, i.e. the acceleration or the change in velocity of the object, to know which law to apply, whether the first law or the second law. When you look at an object and you see that its motion is, in this case, 0, you know it's the first law. So I apply the first law, net force is 0. Then I evaluate the first law by looking at all the forces on the object. 2 forces, N minus mg, they're equal to 0. And that's how I know, let's do it this way. Start there, and then it's kind of, when I do Newton's laws, I kind of think of it in two sides. This is the motion side, and this is the force side. So the motion side, I can see there's no motion. That's how I know the first law. The force side, I have to evaluate. So now let's evaluate it. What are the forces on the object? I have N up minus mg down, and they still equal to 0. And that's how I would know then, that's how I would prove in 3 steps that the normal force equals the weight in magnitude, because I can apply the first law to prove that. So that's an example of that. First law in a vertical direction. Let's look at the car moving down the highway at a constant speed, 40 meters per second, let's say. So here we have the car. It's moving with a velocity to the right, okay? But I look at it and I see that the velocity is equal to a constant. Okay, so if the velocity is equal to a constant, I know that there is no net external force. Because again, there are two ways you can you can have a manifestation of the first law: no motion or constant motion. Remember what we just said: constant motion, constant velocity means the velocity is not changing its direction or its magnitude. So if I look at this and I say that the car is moving with a constant velocity, that means that it does not have a net external force. Therefore, the motion is not changing. So I apply the first law. Net force equals 0. And that's the equation that defines the first law. It's the equation I use. Now, you might see this presented a little bit differently in textbooks. They'll just say this is the second law with no acceleration, which it is, but it's just a matter of perspective. And I think it's useful as a pedagogical tool, a teaching tool, to give an equation for the first law. Some people don't give an equation for the first law, but I do. And from this point on, when I ask you about dynamics, when we're doing considering the dynamics of the problem, I'm going to ask you which law applies, the first or the second. And I want you to tell me by evaluating the motion and then determining. Now, in that question, the third law, as we'll see, talk about momentarily or a little bit later, the third law always applies to every scenario. If there's a force on an object, the third law is applicable. But it doesn't really have a practical equation that we use in solving problems, and I'll talk about that and tell you why. It does have an equation, but not one that's more practical in terms of analyzing problems like this one. But let's finish this, and then we'll come back to inertia. So this car has 4 forces on it. It has 2 in the vertical direction, the same 2 that we talked about here. Has a weight down, mg, and it has a normal force up, the force of the ground on the tires. So normal force straight up. Okay. But it would also have to have 2 other forces on it. It would have to have like the engine force, which I'll call an applied force. Basically, the engine applies a force to the axle and makes the tires go around. But we'll just call that the engine force an F applied, as in an applied force. But it would have to have a force in the same direction of motion. Now, if it only had a force in the direction of motion and no other force, like if it were on a frictionless surface, then the car would accelerate. It would keep increasing its speed because there's nothing to slow it down, right? But in this case, we know that cars can reach a constant speed, which means that there has to be a force in the opposite direction always on something that's on a car like that's on a road or a flat surface. And we know, even though we haven't quantified or defined it, we come into a physics class knowing about this kind of force. It's the force that you use to walk or push or whatever. What type of force would be in the opposite direction, and it would be associated with the wheels in contact with the ground? What kind of force do we call that?
Friction.
Friction, absolutely. We would have a frictional force. Now, we won't talk more specifically about friction until probably chapter 6. But for now, let's at least acknowledge that there is a frictional force, and it's in the opposite direction. And we usually use a small script F to denote the frictional force. Okay, now, you know that Newton's laws or vector equations mean that we can apply them in each coordinate direction. Here, the vertical direction, we generally use the symbol y to refer to the vertical direction. So Fy is vertical. Here, Fy will make that vertical as well, and we'll make Fx horizontal. So we can apply the first law separately in each coordinate direction. Let's first do that for the y direction. In the y direction, again, starting with net force equals 0, I have, again, the left side is the motion side, the right side is the force side. So I have n, basically is the same probably, n minus mg. I mean, let me make a note about this. the symbols, the vector notation. Whenever you have notation that is boldface or using the arrow, the convention is that you're adding the vectors vectorially. So when you have I use the convention that when I have the vector sign, I'm not taking the direction is implicit. So I don't have to explicitly show the opposite direction. But once you relax the vector sign, then you have to put in the sign that distinguishes whether these vectors are in the same direction or opposite direction. So here I'm going to put in the minus sign now that I'm not writing these quantities as a vector anymore, because they are in opposite directions. So ultimately then that will lead to n equals mg for the y direction of this problem, just like for the y direction of the previous problem. Go ahead and just number these equations so I can have something to refer to. Okay, that's the y direction. Now let's do the x direction. Now in the y direction, I know that the first law applies because there is no motion in the y direction. It's not moving along the y direction. Therefore, the first law applies. In the x direction, we actually do have motion, but still the net force is 0 because the motion is constant. It's moving at a constant velocity and its direction is not changing. So that's how I know to apply the first law in the x direction as well. And the first law states that the net force equals 0. Right? Then we evaluate the left side. In this case, I have an applied force, the force of the engine in the direction of motion. I have a frictional force retarding the motion, and they must sum to 0. So when a car is moving at a constant velocity, this tells us that the engine, the applied force of the engine, is equal and opposite to the frictional force. And I have proven that by applying the first law. So that's a basic description of the first law. Whenever something is not moving, or if it's moving at a constant velocity, meaning no acceleration, the first law applies. This is how we apply the first law. Once we apply the first law, we evaluate it to be able to determine certain things about the forces on the object. It's what we use the first law for, to be able to determine something about forces on the objects that abide by that law. Okay, so let's scroll back a bit, and we haven't finished the discussion of inertia. We've defined inertia as resistance to change in motion. And now I think we have a little bit better idea of what I mean by motion. Right? Change in, and what I mean by change in motion. Motion is velocity. Change in motion is essentially acceleration, but without using that terminology, because we usually reserve that terminology for the second law. Change in motion means that the velocity can either be changing its magnitude or changing its direction. Now, yeah, G, acceleration due to gravity. Oh, we don't know about that? Maybe I haven't defined it yet. Weight is, I took that for granted a little bit. Weight is defined as a force, right? Like the weight that you weigh on your scale. And it's defined as it's defined as the mass of an object times the acceleration due to gravity. Now, we defined acceleration due to gravity a while back. We know that objects, we've already talked about the fact that objects of different mass fall at the same rate of acceleration. That rate of acceleration is g, which is 9.81 meters per second. I think I did have this discussion with you before briefly, but I told you we would look at it more carefully when we came back to, when we got to this chapter. I also told you that I would justify to you why an object falls at the same rate even though it has a different mass. But that's the second law. So we'll talk about that when we get to the second law. But yeah, that's the same G that we were using before. And so we're defining weight, W, is the symbol that we use of an object, is equal to the mass, M, times G. That's the magnitude of any object's weight. Its mass times the acceleration of the gravity. Because weight is defined as the force of gravity, or the gravity of the earth on something. That's technically the definition. So this is the mathematical definition, this formula. The qualitative definition really is that weight is the force of gravity. The attractive force of the earth. On a mass. And that's how we define it. So, still trying to lead you to this idea of inertia from a more intuitive point of view. And it's interesting. It's not, you know, the first law is, it's straightforward mathematically, but it's not so straightforward actually to understand qualitatively. And what I found is the best way to really understand the subtlety of the first law is to have a good grasp of these definitions of inertia and actually mass, and understand the relationship between inertia and mass. So back to inertia. Resistance to change in motion. Here's one for you. Here's another thought experiment. This is one I used to use a while back. I haven't used it in a while. It's a thought experiment. Let's say that we are in a classroom. So let's say this is a virtual classroom. It's true. So it's kind of hard to apply this one to. Usually, if I'm in a face-to-face classroom, you know, let's pretend that we're in a face-to-face classroom, and you all are, you know, I'm teaching from in the front of the class, talking to you. But we have access to a space lab classroom. It's 25 miles up in the air. And we've got a space elevator that is attached to our classroom that we can push a button, and at any point we can move up from the ground, surface of the earth, to our space classroom, 25 miles above, directly above us, geocentric orbit, about the point where we exist. So let's say that we transport up to our space classroom right now. I don't know why I'm yawning so much. So we're in our space classroom. But we have these anti-gravity, these gravity devices, not anti-gravity, but so we can, you know, we're up there, so it's, you know, weightless, so things will float around. But we won't float because we have, you know, devices that can keep us attached to our seats, and our seats are attached to the floor. So, yeah. But I have two balls. And going back to two objects of different mass, maybe one is, you know, a massive ball of 1 kilogram, and the other is 10 kilograms. So I put these balls and I suspend them in space, and right in front of them, they're just hanging there. And then I have a device that I can attach, kind of maybe like the rocket thing device on those in the lab that you did, right? And I could take rockets and put them, but I have rockets that have the same force that I'm applying, and I'm applying the force in the same direction. So I have the two balls, and you remember how you were looking down on the top of the lab table there, and you could take the rocket and put it around in different directions. Well, that's what we're doing. We're taking two rockets and we're putting them on the balls, but we do it in such a way, maybe we have a machine that applies the rockets, but it applies them in such a way that it's attached to the balls and are forcing the balls along the same line and along the same angle. So they're parallel and actually the same magnitude of force. And maybe I have a remote that I can cut the engine of the rockets on and off at the same time. So I set that up and I turn on the rockets and the balls start to accelerate. Now one is 1 kilogram, the other is 10 kilograms. And I cut cut on the rockets and I have them accelerate for 10 seconds. Okay, and then I cut off the engine. Now, of course, it's gravity, so they're going to keep on moving after that, a different type of motion. But let's say that just during the time when I am have the engine on, technically it's the second law because that's a net external force. But my question to you is, so in that case, clearly the motion changed and it will continue to change while the balls were accelerating. And it did so for a certain amount of time, equal amount of time for both objects. Let's say Muhammad, after the end of the time period, the instant that I cut the engines off, which ball will have traveled farther, the 10 kilogram ball or the 1 kilogram ball? And remember, before you answer that question, the force, the rockets are situated so that the balls are traveling parallel to one another, that is along the same line and in the same direction. And I power the balls, basically the same amount of force for the same amount of time has acted on each ball. So after that time period, and I made an arbitrary time period, I didn't give you a specific time, it doesn't matter. But the thing that does matter is that it's the same amount of time that both balls were exposed to the same force. After that time period, which ball would have traveled farther, Muhammad?
Probably the 1 kilogram ball.
Yes. Why, Muhammad?
Because it's smaller and it goes faster.
Because it's smaller.
Yes.
That's true. What about what is that? Can you? Yes, Daniel?
But you said it is the same force, right? The same force, like
yes.
you apply the same force. Shouldn't
yes.
both of them reach the same time?
Why do you say that?
Because you applied the same force,
I applied the same force to two different masses.
Yeah.
Let me ask you this, and I'm gonna come back to you, Muhammad, so hold that. So talking about the same force, if you apply the same force to a car as you apply to a child's wheelbarrow, do you have a different action, a different response?
Yeah.
Okay, you're applying the same force. Why would you have a different response based on your logic?
Because this one is lighter and this one is heavier.
Okay, so you use lighter and heavier. I would say you're on the right track, but lighter and heavier implies weight. And it's not the weight that's the issue. Let's go back upstairs, now I'm gonna stay with you for a second, Daniel.
Okay.
I'm coming back, Muhammad. But Daniel, with you. So when you go to the classroom, again, you have a 10 kilogram ball and a 1 kilogram ball.
Yeah.
Do you see a correlation between the same force being applied to those and having a different reaction as you do with the car and the wheelbarrow on the ground?
No.
Why not?
Because the class, it should be heavier, right? The class. You're talking about the you said the elevator taking us up. Is that what you mean? And applying the same force to the elevator taking us up to the space?
No. We're in the class. We're up there. I just laid out a whole experiment where we're talking about a 10 kilogram ball and a 1 kilogram ball. What are you talking about the elevator? No.
Okay, go on.
I'm saying we're back in the classroom and you're applying the same force. So I'm asking you to reconsider that I've applied the same force to the ball of two different masses. Initially, you said that they should be the there should be no difference in their response to the
Yeah.
same force. But when you went to the ground, you said there should be a difference to a response to the same force of objects that have different masses. So I'm saying, what is the difference in your mind between applying to the experiment on the ground as opposed to the experiment in the classroom?
Because like this one is on the ground moving forward, but the classroom is going upward. You know, I said that because like, you know, in the forklift, you know, something like that, in the forklift, if you put a different mass on the left and a different mass on the right, as long as it is on the forklift, both of them are going to go up at the same time. And, you know,
Daniel, I don't know how you started talking about this elevator. The elevator just gets us to the classroom. The thought experiment in the classroom are the two balls, the 10 kilogram mass and the 1 kilogram mass. We're not talking about an elevator.
okay, no, I understand what you're saying. You're talking about like why I said different force is going to act differently on, you know, on the ground, and why the one is going to act upward. Like that's what you're saying. Like,
No. Why? But I'm not comparing it to going up. I'm saying the analogy on the ground was to be compared to the two balls in the classroom in the elevator. Two balls in the classroom, not the elevator. Has nothing to do with the elevator. I mean, we might be able to design some thought experiment where we compare that, but I didn't do that. So when I said back in the classroom, I'm asking you to compare the scenario of the two masses on the ground with the constant force to the scenario of the two masses in the classroom with the constant force. Forget the elevator.
okay.
Do you not see an analogy between the example I made in the classroom and the example on the ground? The analogy is that there's two masses being applied to a constant and a constant force applied to them. It's a simple analogy. I think you're overthinking it.
Probably, yeah.
But clearly you made a distinction between the same force being applied to two different masses on the ground. I'm simply asking you, why don't you make that same distinction to the two masses in our classroom up in orbit? What's the difference of that in your mind? I don't get it. Do you understand what I'm asking?
Actually, no. You're talking about the two balls in the classroom, and like the same ball on the ground, like on the floor. Hello?
Yeah, it's not the same ball. I mean,
Yeah.
we could make the same ball, but I had given, just to emphasize the point, I had made it a car and a wheelbarrow.
Yeah.
But yes, I'm comparing the car and the wheelbarrow on the ground to the 10 kilogram ball and the 1 kilogram ball in the classroom. Again, you don't see that. Go ahead.
I see it now. So I'm saying for the wheelbarrow and the car, if you apply the same force, the child's wheelbarrow is gonna like go higher faster because like it is lighter. Then
That's right.
yeah, so on the two balls in the classroom, the 1 kg ball is gonna go higher than the 10 kg ball because it is also
Okay. All right, wonderful. That's what I'm getting at. And again, we're talking about, we're not moving up. Like, I think maybe that's also what threw you. And I didn't draw it, so that could have threw you off. We're moving in a horizontal direction.
okay.
So it's not up or down away from the earth. That could be a little bit more confusing. On the ground, the forces are applied horizontally. So we're determining how far they would move in a horizontal direction. Same thing in the classroom. We're doing it horizontally, implying parallel to the surface of the earth. So in either case, the force of gravity has nothing to do with the motion. It's just like this, in this case, we're moving horizontally. So the force of gravity is not going to determine how far the object moves in a horizontal direction. That's the same thing that I'm applying. Yeah, so that's what I'm getting. And coming back to, yeah, good. So Muhammad had correctly answered that the lighter ball would go farther. Okay, and so now you're on the same page. So I hope as everyone on the same page before I go back to Muhammad, because we're still not finished with this. Everybody got what we're doing and what the result is. And so I agree that the ball with less mass will move farther. Okay, thank you, Daniel. But here's something that I want to distinguish between what you said, Daniel. You said the lighter ball will move farther, and it will, but not because it's lighter. In other words, there's a distinction between weight and mass. The term lighter or heavier implies weight.
Yeah.
We don't really have the same terms in implying mass. Mass, we just say more mass or less. But if you say heavier or lighter, you're not implying mass, you're implying weight, and there's a difference. Weight is the force is G times a mass, but mass is just mass, right? Mass, actually, in terms of this perspective, mass is actually weight divided by the force of gravity. It's very different. Weight is a vector quantity. It has direction, magnitude, and direction. Mass is not a vector quantity. It's just a number, right? So that said, Muhammad, let me ask the question, the second question I asked you, which has to do with this implication I was making here. Why does the smaller object move farther under the same force?
Because when it's small, it has lesser weight than the force that has a lot bigger one, so that'll be easier to go forward.
Well, that might seem to be the case. That's the same answer that Daniel gave. But the problem I have with that is that we're 25 miles up. And the objects were, when they started, they were floating in the air. That's right, there's no gravity. Who said that? Abdul, that's right, there's no gravity. So you can't talk about weight. Both of them are weightless. So the answer to that is no, it's not the weight that's the distinction. Abdul, what's the distinction?
It's because the pull of gravity is not acting on those objects.
Okay, that's why it's weightless. But that's not the answer, Abdul. My question is, why does the smaller object move farther? Well, Daniel, you say acceleration, but that's also the same question, or Dami. I didn't ask that, I asked in terms of distance, but which object, you could ask that as well. Which object is moving faster at the end of that time period? The smaller object or the larger object? The smaller object. So that's basically the same as saying, I could ask the question slightly differently. Why? So if the smaller object is moving faster, that means that it increases velocity more in the same amount of time, which means that it has a larger acceleration. So I could ask the question this way: why does the smaller object has a larger acceleration? So in that case, you couldn't answer the thing by saying it's acceleration, right? So it's not about the acceleration. The large acceleration is a result. The force is constant, it's the same.
Is it because the mass is smaller?
It is, and someone said that, or I think Roy said that earlier. Laura, I saw, I didn't have a chance to get back to you, Roy, but Roy said that I think first. And yeah, Roy, you're right. And now you also are right, Daniel. It's because the mass is smaller, not because it has a lesser weight. Neither one has weight. It's because mass is smaller. Now we're getting someplace. Because also, Abdul, someone talked about acceleration. I forgot who that was now. Honestly, who was that said something about acceleration? That was Dami, yeah. So let me ask you this. We have defined, the first law is the law of inertia. Let's go back to that term now. In this thought experiment, we have determined that the less massive object has moved a farther distance in the same time period. And by implication, we've also said that at the end of that time period, the smaller object is moving faster, which means that it has a larger acceleration during the time in which velocity was changing. They both had an initial velocity of 0. At the end of that time period, the object has moved farther and is moving faster. And that's why it's moved farther, because it was speeding up faster at time period than the more massive object. Why? Because it had a large acceleration. Okay, let me ask you this then. Given those two results from our thought experiment, which object has more inertia?
The 10 kg.
Okay, everybody said yeah. Yeah. Everyone says not heavier, more massive, bigger. Yeah, everyone is saying that. Yeah, the 10 kg, Dan, that's right. The more massive object has more inertia. Why? Because inertia is resistance to change in motion. Which one resisted the motion more? The 10 kilogram object or the 1 kilogram object? Well, obviously all of you now see it's the 10 kilogram object. How do you know that? Because by the same force being applied, at the end of that time period that the force was applied, the larger object had moved the shortest distance and it had the smaller velocity, which means that during that time period, it had the smaller acceleration. But the same force was applied. So the larger, more massive object resisted that force, or the change in motion that that force was trying to activate on the object, more than the less massive object. So now I think all of you understand what inertia is. It's a very esoteric quantity. It doesn't have an equation, but it's a very significant quantity to understand. And the thing is, even more subtle about it, is comparing the thought experiment in our classroom in orbit as opposed to the ground. You might be tempted to think that, again, that it was the weight of the car that caused it to be more massive, or to have more inertia. Or you might think it's friction, because it's heavier, it's pressing to the ground harder, so there's more friction. But if you took those same objects up in space, the car and the wheelbarrow, just like we had the two different masses here, and perform that same experiment, you're going to get that same result. That the wheelbarrow will move farther than the car, and obviously then it has nothing to do with weight or friction, because none of those things are applicable when the car is in orbit. It's because of the mass of the object. The mass is what contributes to the inertia. Now, so that's it. Roy, Jesus, I don't know. No, Shura. So, Shura, can you tell me again, what is inertia? Define inertia for me.
Inertia is the first law of motion, so it's like the resistance between any form of resistance of the form of motion that it is currently doing. So if it's at rest, any type of resistance try to make it move, it will continue to be at rest. And if it's moving, any type of resistance try to stop it, will continue moving or so.
That's right, but let's make it even more succinct now. You don't need to give the anecdotals. You can just tell what inertia is. And inertia is this. Inertia is defined as resistance to change in motion, period. That's all you need. Yeah, those other examples kind of explain it, but you don't need all that if you understand it. Inertia is resistance to change in motion. Now, also, sure, I want to, you were, I guess correct in that, and associating the inertia with the law, with the first law. But the first law is not a definition of inertia. The first law and inertia are two different things. In fact, you don't even see the word inertia in the first law. It's called the law of inertia because of what you just said and because of what I explained, but they are two different things. The law of inertia is the following. An object will stay an object will remain at rest or in motion in a straight line unless acted upon by a net external force. Nowhere in there did I use the term inertia. So clearly inertia and the first law are not the same thing. Why does Newton call it the law of inertia? Because of what happens if a net external force. You get different types of motion, even if the net external force on two different objects is the same. That leads to the definition of inertia, understanding that result, and that is that inertia is resistance to change in motion. So, law of inertia is what I just said. Inertia is resistance and change in motion, period. Now, Roy, if you're there, I want you to give me a definition of mass. We've described in the law of inertia. We've defined inertia. I want you to now just define mass for me. What is mass? I'll answer that question in a minute, Abdul. Roy, are you there? Yeah. So, can you define mass in terms of the discussion that we're having? Go ahead, define it then. Yeah, no, I didn't define it. Okay. All right. Jesus, are you there? Okay. David
Yeah.
Edwards. Oh, sorry.
Yeah.
Go ahead. That's all right. Jesus, can you define mass?
No.
Think about what we just said. So let me help you a little bit, both of you. So we just said that inertia is resistance to change in motion. And the 10 kilogram mass had more inertia, everyone agreed, than the 1 kilogram mass. Everyone agreed with that. Let me ask you this, Jesus. Let's say that you have an object that is, let's say an elephant. Say we have an elephant and a lion. Which one has more inertia?
Elephant.
Why?
It's heavier.
Okay, not heavy. What if they're in space? Which one has, what if they're floating?
More mass.
So say that again. More mass.
Yeah.
That's right.
Okay.
Because the elephant has more mass. No, I wouldn't say that, Dieter. No, because mass can exist. I would say that about weight. Mass is something that we'll see that mass is an inherent quantity of an object. It doesn't change no matter where you are in the universe, but weight does change. So Roy, that's inertia. Inertia is how much resistance an object has to moving. So the inertia is the resistance to change. Oh, how much? Yeah, yes, that's right. It's how much it is. Good. Yeah, so you're right, Roy. That's it. That's the definition of mass. And I would say a little bit differently, a little bit more succinctly, that mass is a measure of inertia. It's the way to measure inertia. It's the direct measurement. That's how you knew, Jesus, that the elephant had more. You don't know what the elephant, how much mass it had, but whatever it is more than the lion, so it's got more inertia. So by measuring the mass of the lion, you're actually measuring the inertia.
Okay.
Professor.
Yeah, and that's how it can resist more, Roy, because it has more mass. Yes, David.
Professor, please, I'm confused. Can you really like do an analogy of mass and weight? Like what is weight? How is it different?
I can, and the qualitatively is just what I said. Mathematically, it's this equation right here. Clearly, they're equal, but like mass can't be equal to weight if it's equal to weight divided by the acceleration due to gravity, right? So just from a mathematical point of view, you can see that those weight and mass can't be the same thing, right? So that's quantitatively, but that doesn't tell you everything about it, right? That doesn't really tell you the definition. It just tells you what you just asked me, which was the difference between mass and weight. It doesn't still tell you then what mass is. We know that weight is mass times acceleration due to gravity, but then looking at the fact that weight is divided by gravity is equal to mass doesn't tell you what mass is. In order to understand what mass is, basically Roy got it. You have to understand what inertia is, right? So let's go through the definition because it's just that simple for what I said. And you have to understand the subtlety. The law of inertia is an object will remain at rest or in a straight line unless acted upon by a net external force. Inertia is resistance to change in motion, period. That's what it is. Now, what is mass? Mass is simply a measure of inertia or a measure of resistance to change in motion. And that's it.
So, Professor, now, if I'm trying to do something on a
Yes.
scale, is it a weight or a mass? If I'm weighing like 5 grams on the on the scale, is it weight or mass?
That's mass. You're measuring mass.
So when do I
You're
measure
measuring mass.
when do I measure weight?
That's a very good question. It's a very good question. And the answer is you basically are always measuring mass. Whenever you have a scale that gives you weight, what it's doing is measuring your mass and then converting it to weight by multiplying your mass times g. It's just doing it so you don't have to do the calculation. It's calibrated that way. But you're always measuring mass. Mass is actually the only thing you can measure. But then you figure out what the weight is by multiplying by g. And there's some devices that do that kind of automatically for you. So it makes you think you're measuring weight, like when you get on a scale, but you're not. I mean, it becomes kind of an argument, a pedagogical argument. Like, are you measuring weight or are you measuring mass? In the end, I would say you're measuring mass and then converting it to weight. That's the way I would say it. And this is why. Because when you go to the moon, does your weight change?
Your weight? No, I don't know. No.
The weight does not change.
Your weight, I think your weight is constant, right?
So
mass.
David says yes. Dami says yes. Jesus. Jesus says mass changes. Roy says yes. So let me straighten it up. The weight is defined as the force of attraction of. Actually, I said Earth, but it's not true. It's any gravity. The weight is the force of attraction of gravity on a mass. So yeah, if you're on the Earth, it's the Earth's gravitational attraction. But if you're on the moon, it's the moon's gravitational attraction that defines your weight. So is the gravitational attraction larger on the moon than on the Earth, or smaller than on the moon than on the Earth? Anyone?
Smaller.
David. It's smaller. So if you were go to the moon, if you were on a scale and measuring your weight, would your weight be larger or smaller or the same?
Smaller.
It'd be smaller because the moon is pulling you to its surface with less force. Yeah, it's smaller. So the weight changes. But does your mass change? If you are measuring mass on the Earth versus the moon, would your mass be different? Dami says no. Good. Roy says no. Anybody else? Yeah, I do. Everybody says no. And yeah, I agree. No. Why? Well, that thought experiment that I just did at the beginning of this discussion proves it, right? Because mass is resistance to change in motion. So my resistance to change in motion would be the same on the moon as it is on the Earth. My mass doesn't change. In fact, that's one thing we can say now that we have defined mass. We can make a statement about mass. That mass is an inherent property of an object, meaning that everywhere in the universe, the mass of an object is the same. It's inherent. It inherently describes that object, whereas weight is not. Weight is dependent upon external forces that are affecting that object. So they're not inherent to the object, and they will change depending on where the object is in the universe, depending on what those external forces are, like in the case of measuring the weight on the Earth versus the moon. So mass is an inherent property of an object. And because mass is a measure of inertia, you could also say that inertia is an inherent property of an object. The inertia of an object, the resistance that it has to change in motion, doesn't change. So if I have a force that you apply a force to me on the Earth, right? And assuming it's the only force, so take away friction, take away drag, drag and all that. Drag is, and someone said something about drag, and I didn't answer that question. I'll go back and answer it. But let's say that you're, on a frictionless surface, and you're in a vacuum, and you have a force. Like say that we take that experiment that I did in the classroom, and I did something similar on the Earth, where say I put two objects on ice or on some frictionless surface. Doesn't have to be ice. I applied a force, and they're in a vacuum, so we're not considering air resistance. And we're horizontal, right? So we're taking the gravity out of it, the force of gravity out of it. Just like this scenario here, force of gravity is vertical, other forces are horizontal. So like in this case, I take a frictionless surface, so there's no force there, and I'm doing an applied force in the horizontal direction to do different masses. Well, let's say one mass. So after a certain amount of time of applying that force, I look at the distance that I've traveled and the speed that I've traveled on the Earth. But then I go up to the moon and I do that same experiment with the same object. Frictionless surface in a vacuum. Would there be a difference, and I apply the force for the same amount of time. Would there be a difference in the value of my velocity after that amount of time? And would I have traveled a different distance on the moon given the same force applied for the same amount of time? Shora, what do you say?
Sorry, can you repeat it again?
Jesus, I think, answered. So Jesus, you chime in. What did you say? No? No, because can you explain that to Shora? Are you there? Oh, maybe that was a different question. I don't know. But sure, yeah. I have an object on the ground. I apply a force to it, and it's on the frictionless surface, and it's no air resistance. After a certain amount of time, I measure how fast it's moving, and how far it traveled, assuming it started from rest. I go up to the moon and I perform the same experiment. Same mass on a frictionless surface, apply a force to a certain time period. Same time period that I did on the Earth. At the end of that time period, when I look at the distance traveled and the velocity of the object, how does it compare to the data that I collected from that same experiment on the same mass on the surface of the Earth? For example, does it travel farther or the same? You say farther?
Yes, it will travel
And what about the
further
velocity?
because the velocity, because it's not deal with gravity, will be greater than that on Earth since it's zero gravity versus Earth's gravity, which is 9.81. So that force will be
Well, it's
working
not zero.
against it.
So a couple of things I'll say about that. That first of all, it's not zero gravity on the moon. It's just less gravity. And secondly, as I showed here, gravity is acting in the vertical direction, not in the horizontal direction. And those thought experiments that we considered previously, we didn't say anything about gravity.
So in that case, because gravity is not a factor, so because gravity is not a factor, so there is no opposing force going in the same direction, would they be equal then?
They would be equal. They would be equal. Why? Because the only thing that's causing a difference in motion, as we showed with the first experiments, is that the mass was different. And because of that, inertia was different, the change in inertia, the resistance to change in motion. In this case, with the same mass on two different environments, horizontally, gravity is not in effect. It's just the force along the direction of motion, right? That is affecting its motion or change in motion. And then the only thing that's going to cause a difference is if the resistance to change in motion has changed. But I just said I'm using the same mass. And mass is an inherent property of the object. So the mass doesn't change just because it goes to the moon. So on the moon, it's going to have the same inertia under those conditions that it does on the Earth, even though the force of gravity is different. But the force of gravity is not affecting that direction of motion because it's horizontal, it's perpendicular, and the force I'm applying is horizontal. So that reinforces the idea that mass is an inherent property of the object, and so is inertia, because mass is a measure of inertia. And anywhere in the universe, the inertia of an object and the mass of an object will be the same, provided there's no deformation of the object. You're not breaking it apart or damaging it or anything, or taking some other way, whatever. So that's the distinguishing factor between mass and inertia, and also describes the first law of inertia. And this is the way that we kind of apply the first law of inertia. We have many more examples of that, but this is the introduction. Now, someone had asked about the difference between weight and mass, and I gave a short answer. We can talk about that a little bit more when we get to the second law. But I want to justify it only in terms of the implications of the first law, because that's what we're talking about right now. So in terms of the first law, that's about the best way I can explain it. Technically, this is already getting into the second law, but still. Yeah. Now, someone had said something about air resistance a while back. The question is going about my vision. Oh, here it is. Could you go backwards and say a mass is an object that hasn't had that force of gravity? Oh, no, that's not it. It was something about air resistance. I don't know. But whatever that question was, hopefully this. I've kind of cleared it up in the process of this other discussion.
The question
air resistance.
The question said, can air resistance be considered as inertia in a free fall object example?
Okay, good. Yeah, thank you, Abdul. So again, so Abdul, tell me, how did we define inertia? what is inertia?
Resistance to change in velocity.
Abdul, or is that?
Resistance to change in velocity.
Yeah, yeah, but I'm saying you're the person that asked the question about the inertia and air resistance, right? Initially, or no?
Yes.
Yeah,
I know. Yes.
yeah. So yeah, so you're right. I would, yeah, resistance to change in velocity. Yeah, I would say it more generally, more. Yeah, Newton would say resistance to change in motion. But yeah, we've identified that motion as velocity as 3 minutes. So yes. Okay. And we've said that in order to measure it, so that's a qualitative definition. If you want to quantify the term inertia in any way, the only thing you can do is basically measure its mass. So if mass is a measure of inertia, then we're kind of saying, they're kind of the same. They're not really the same thing, but quantifiably, the only thing that you can say about inertia in terms of quantifying it is measure its mass. And its mass is measured in units of kilograms in the MKS system. So when you make the way you write this statement, can air resistance be inertia? Well, air resistance, what kind of quantity is that? Physically, what type of quantity is drag or friction?
Quantity.
Say again? I didn't hear you. You cut off. What? I can't hear you. Can you say again?
The drag. It's like considered
I'm
as
asking
drag.
what type of force is that? Yeah, okay. Yeah, air is drag, but what type of force, well, I just gave you the answer. I was trying to ask what type of quantity is drag in terms of dynamics. Well, you may not know. I don't know, or may not. What I'm getting at is that drag is a force. Resistance is a force. Friction is a force. It has units of newtons. Do you see that or understand it or believe that?
Yeah.
Yeah. What type of quantity is mass? I think what is the units of mass?
kg.
Kilograms. That's right. So that's like comparing apples and oranges. An apple is not an orange is not an apple. A force is not mass. Mass is not a force. They are related, but they're not the same thing. So the short answer is that no, air resistance cannot be considered inertia because inertia is associated with mass. It's not really mass, but the only way we can quantify it is by measuring mass. So if you could qualify it, the only thing that you could say is that, an object has, more inertia because it has more, kilograms than some other object. So inertia and drag are not even, they're like apples and oranges.
Got it. Thank you.
Because they're different units. Yeah. Anything else on the first law of motion? All right. Well, I guess we're at 2:30 or past it, so that's break time. And this was a really nice discussion. Discussion of the laws of motion are always like that. Well, the first law and the third law, it's really more discussion than practical application. There's a lot of practical application with the first law, but people ought to incorporate that into the second law. But we'll get to that in the second law. But the second law basically is probably the most well-known for the reasons that it's maybe the most pragmatic, the most practical. And so we'll have discussion about that as well, but a lot of problems that we'll be able to work out essentially between the first and second law, but not until we define the second law. So here is more kind of well, we can do statics problems. There's statics problems we can do, actually. But I think what I'm going to do is wait until maybe we do a couple problems on this before. Sure, maybe we can do that. I did a couple here. It was a very easy, just engine. Maybe I could do one more. So let's go ahead and take our break right now. Yeah, take our break right now. When we come back, yeah, we'll do some practical applications of the first law. Statics. Yeah. Probably right, because there's a couple other things I can say before I finish this introduction of the laws in general, and then we will we'll do some applications of the first law. Let's take okay, it's 10:40. So let's take maybe 15 minutes. We'll come back maybe 5 till or 15, 20 minutes. God. All right, cool. Great discussion. We'll be back in a minute. So that's the activation code for the for the labs. Yeah. Okay, let's do a couple problems. Sorry, finish this. Doing this introduction of forces, so we've done mass, we've described that. So we have inertia, we have mass, we have law of inertia. So there are 4 known forces that we have identified in the universe. We call these forces fundamental forces because they were presumably there at the beginning of, at the Big Bang or within a short period of time after the Big Bang, they were formulated. Does anyone know what the 4 fundamental forces are? Let me just give you, push you on through. The 4 fundamental forces. They are gravity, gravitational force. Now, it used to be 5, electricity, magnetism, but electricity, electrostatic force and magnetostatic force were combined in around 1860 or something like that by James Clerk Maxwell. I mentioned that before, I believe. So electromagnetic force is now considered one force, combined force. Then you have the forces that basically hold matter together. And loosely speaking, strong force, strong nuclear force, and a weak nuclear force. Yeah. Now, grand unification is an idea that all these forces come from a single universal force. grand unification was an idea that was, I think, first proposed by, well, it was first pursued by Einstein. I think someone actually proposed it a while back before Einstein, or maybe he proposed it early on and then came back to it when other people started kind of gravitating toward it. But ultimately, he spent the latter portions of his life trying to unify the forces. And to this day, we haven't unified all of them. I think in the 60s, maybe these two came together. I forget the order. I have it here. Yeah, I don't think I have it. I should look it up real quick. The weak force and electromagnetic. Let me see. Yeah. It's called the electroweak force, which is yeah. Right. I guess that's what I would have said. The weak nuclear and electromagnetic were combined. So these guys were together first. And then I should do it like this. Remember the years of the circumstances, but we just couldn't map it out. So weak. These guys were together. And then at some point, the strong came on. Now we have not put the gravity with everything else yet, but picture here is implying that we have. Yes, it's a projection. No, so right. Let's go in the opposite direction. Yeah, so I don't remember the timetable, but weak and electromagnetic were combined first. And at some point, strong nuclear with those two. But we have gravity, which is obvious, which seems to be the force that is the most well known, is the least actually. It's the most. It's probably the first gravity. Obviously, was the first force that we kind of became aware of. But it turns out it's the most subtle to actually fully understand. And so grand unification will be the unification of gravity with the other known fundamental forces. you know, like there's much more, well, you might have heard of dark energy, dark matter. The idea is that there is more matter in the universe than gravity can account for. For example, whenever we'll learn later on this semester that, well, actually it's in physics 39, that light actually has momentum. And so it can be affected by forces like gravity. So, and we know that because whenever we see light coming from a star or a planet or something, you know, like a star, I guess, you know, we can take pictures of that with the telescopes that we have up. We have 3 different types: one that does visible light, the other does infrared, and then one does X-rays. We put those 3 different types of light together, combine the pictures, and we get these magnificently beautiful pictures from the 3 different telescopes. Hubble is the visible light, and I forget the names of the other 2. But so we can take pictures. You know, the light's coming. You know, it takes eons, light years to come from stars. You know, very far away. And the light we actually see is millions, you know, of years old and that sort of thing. All side points to the point I'm trying to make, which is that whenever light passes a massive body, so it's coming, you know, from someplace in the heavens, and it passes things like stars or black holes, and it might pass close by from our field of vision. So light's coming from a star, but there may be like a black hole in between here and the star, or, you know, a galaxy between here and the star behind it, or a galaxy behind that galaxy that we're trying to see. And what happens is that the light, when it gets to a massive body, it bends. The light bends toward that body. You can even see it like with our sun. Like in the light, something behind our sun, the light's coming toward it, you know, it bends. And maybe that's how they figured it out, because, you know, maybe we're looking at something as we go around the sun, and our field of vision is different at one point in our orbit than at another point. And so we can tell that there's a shift in the light as we move, you know, the visual angle increases as we get farther away from the direction in which the light is passing by the sun relative to our field of vision as we're looking at it. Anyway, the point is that light can bend. We know that. But when the light is coming by galaxies that we're somewhat familiar with, like Andromeda or something like that, you know, the closest galaxy, based on how big we can, you know, based on the amount of objects in the galaxy that we can see, the light bends more than it should, because we're assuming that it's being bent by gravity. Gravity can bend light, right? Because light has momentum, and if it's bending more than it should, meaning that there is much less gravity in the galaxy than is accounting for the amount of distortion or bending in the light that's passing it. And this happens consistently over and over again. So at some point, and then if you look at all the galaxies in the universe, there's much less mass in the galaxies of the universe that, as we've computed it, than what is apparent by what we see. And so people think that there is more mass in the universe, most of it, which is invisible. And so that's the idea of dark matter. Someone proposed the idea of dark matter years ago, and we've been looking for dark matter ever since. Was there a question, Roy, about, what was that? Gravity? What was the question? Gravity and electromagnetic. like electromagnetic force, strong force, weak force. That's what you're asking now. Anyway, that's one of the issues with gravity now, is that we think there's more than there should be, and we're looking for something that's called dark matter, which is supposed to be the matter that is responsible for the extra gravity in the universe that we can account for. The other thing is dark energy, and the reason I kind of mention that, even though it's not force, is that anytime there is a force, there has to be a field associated with the force. And I mean, they're just calling it gravity, but there's also energy in the universe, more energy than is accounted for. I just mentioned that since we're on the subject. Basically, we know that the universe is expanding. And just for the record, so that you understand this a little better, I'm sure you've heard this term before, that the universe is expanding. But what you may not understand about it is that it's not expanding in the way like a bomb would expand. We'll look at exploding particles and we look at conservation momentum in a couple of chapters. But you know, the idea of a bomb exploding is like, say you have an object, that a firecracker or something like that, that explodes into two parts. Well, there's a center of mass, so the thing is moving along and then it explodes. Where there's a center of mass that actually doesn't move, let's say that's, you know, the bomb is like stationary and it explodes. The center of mass, because of conservation of momentum, stays at the same place. And the objects are moving away from that center of mass as it explodes. So when people think about the Big Bang, they may think of it in that way, that, you know, there is space, and then there was this ball of energy, and the ball of energy exploded. And now everything that was in that ball of energy, or it's not a ball of energy, it was like a point particle of energy. The whole universe was in a point, is the idea of the Big Bang, and that it exploded. And then now all these particles are moving away from that central location where this, you know, this infinitesimally small universe or was that prior to the Big Bang. So there's a couple things wrong with the way that I said that. One, space did not exist. You know, the point particle that exploded did not exist in space. Space was also a part of that point particle. Now you might ask, well, what was around there before the Big Bang? What was like that thing in? I don't know, but it wasn't space. I can tell you that. Not space in the way that we define space now. It was something else. Basically, the only answer you'll get is that there was nothing there. So you might ask, well, what is nothing? I don't know. It just wasn't space. So the idea to think that space existed and then the Big Bang exploded and all the stuff in the universe now expanded into space is an incorrect assessment. The space that we now look of and call space was also inside the Big Bang. Right, so yeah. So because that's true, when we talk about the universe expanding, it's going to trip you out, but this is true and this is what it is. It isn't just that the objects inside the universe are expanding, like the galaxies and the dust particles and the stars and all the stuff. They are expanding. But the fabric of space-time itself is also expanding because it was part of the Big Bang. Just let that sink in for a minute. When we see a galaxy or another galaxy, if you look at the velocity of all those particles, what it says is that those particles are moving away from one another. But another corollary to that is that every particle in the universe is moving away from every other particle. Now, the only way that that could actually happen, if you think about it, because that doesn't really make sense, if you're thinking about those particles moving away in a stationary object like space, like the idea of, the idea of these two particles expanding, like, so when you think of a conventional firecracker, it blows up and expands. Well, the space around it has nothing to do with those particles, right? The space around it is different than those particles that are one particle and exploding. So what we think of is that those particles are exploded or expanding in space. That is really, so it's expanding in space. The Big Bang, no, that space was part of the particle before it exploded. So now everything is expanding. The fabric of the universe and everything in between the actual particles that we're calling galaxies, the stars, or whatever. That thing between them is also expanding. And that's why when you consider that, all the objects themselves are expanding away from, think of it this way. Let's say that if you take a snapshot of the universe, and at this point in the universe, all the particles in them, the galaxies and everything, were not moving. They were pinned to their position in space. And they didn't have their velocities independent of the fabric. So everything is stationary. But then you take space itself and pull it apart. Well, clearly you can see that if you do that, even though those particles have no independent motion, the thing that they're in is expanding. So they're going to start to move away from one another. It's kind of like if you take a balloon, right? And you blow it up a little bit, and you put marks on the balloon, right? Dots of ink marks on the balloon. Then you blow into the balloon. Well, it's clear those dot marks are not moving. But then you blow into the balloon itself expands. Well, each particle then is going to be moving away from one another simply because the thing that is on is expanding. Okay, that's what space-time is doing. Now, in addition to that, somehow if you could make those dots that you have, that you place on the balloon, move around independently of the balloon moving itself, then now you're getting a better picture of what space is actually doing. That all the objects in space have individual motion, but because space-time is also expanding, underneath that motion is another expansion. That's how complex it is. And the amount of energy that the Big Bang had, that we think the Big Bang had by current theory, when you account for that, basically there's conservation of energy, which we'll talk about a little bit later in chapter 5 or 6 or 7, whatever, later. There was a certain amount of energy that the Big Bang had before it expanded. Well, conservation of energy says that you can't create or destroy energy. So in a conventional sense, going back to my bomb and my two particles, there's energy in there. There's chemical energy. It blows apart. Now that chemical energy has become mechanical energy, which you can account for all the energy. Some of it is potential because of positions are changing. Some of it is kinetic because there's motion. But some of it is also heat because there was heat escape when the thing blew it up. All of those energies, the heat, the potential, the kinetic of those two particles, if you account for all that energy, it must be equal to the amount of energy that was in chemical energy was in the bomb before it exploded. Conservation of energy. Same thing happens, it must apply to the Big Bang. There was energy inside the point particle that was the universe before the Big Bang. We can theoretically determine how much energy people have, determine theoretically about approximately how much energy that is. But when we look at the universe now, even though we can't see everything, we can theoretically, based on what we can see, we can theoretically approximate how big the universe is, and therefore how many particles are in it, and therefore how much energy all the particles have, and therefore how much all the energy is in the universe at this instant, based on how much is expanding, the potential energy, kinetic energy of all the stuff, plus all the other energy interactions. We can theoretically do that. When we compare that energy to the energy that the Big Bang had theoretically, there's almost no comparison. There's much more, not just like way beyond the fraction of error. There's much more energy in the universe as it expands than what we calculate that was in the Big Bang. So much so that that basically the universe supposedly is like, there's a couple of different theories but the one with, giving that there's more energy than there should be, is that the universe is expanding faster than it should. And so it's never going to contract again. So basically, like, the idea is that if there is conservation of energy, right, then there should be a yo-yoing effect in the universe. Like the Big Bang, it blows up, it goes apart, it expands, but then the particles are slowing down. At some point, they're going to lose all the kinetic energy, and then the gravitational energy is going to bring them back together. And basically, at some point, the Big Bang is going to come back again. And some people say that it'll just happen over and over again. That the universe is just this thing like a yo-yo, that it blows up, expands, come back together into a small ball, then blows up again, expands, come back into, just keeps doing that for whatever. I don't know. That's the theory. We don't know, but that's one theory. But one thing that contradicts that theory is that when you look at the energy that it has at this instant, is more energy than it supposedly had when it began. So where is the energy coming from? And so people don't know. We're trying to figure it out. And that's, if you heard the term dark energy, that's what that is. It's the energy that's not accounted for, that we don't know where it's coming from. Yeah. So that's dark energy, which is specifically relevant to this thing, to what we're talking about. And because I started talking about dark matter, which is specifically associated with what we're talking about in this lecture. But because I was talking about dark matter, I thought I would just throw dark energy in there and explain that as well, which is not specifically based on conventional thinking associated with what we're talking about. But I just wanted to clarify what those are. Now, I'm going to add on to that. Conventionally speaking, people don't necessarily associate dark energy with dark matter. Like, they're two different problems that are not, based on conventional thinking, are not necessarily related directly. I happen to believe that they are related. That one, so what we'll find when we get to work is that any kind of conservative force always has a field associated with it. A conservative force, we'll talk about what that is, but like a gravitational force also has a gravitational field. The field and the force, now I know you kind of use that term interchangeably, like you might say, before you came into this class, you might call something like in Saturday morning cartoons, they'll talk about force fields. That's kind of technically speaking, a force doesn't have a field. There's no such thing as a force field. There's a force, and then there's a field. Because a field implies that the thing is there, whether or not there's anything else there, as we've been talking about with electromagnetism, right? That when we did that problem earlier, there are forces on those charged particles, but the forces are only there when the charged particles are in proximity to one another. If I take one particle and take it very far away, there's no force now, right? Because there's nothing that this charge can force upon. So, yeah, but the field is there in both cases. The one charge has a field that goes out to infinity. And when I bring in the other charge, it has a field itself. And the combined fields, as we showed with the dipole the other day, like it also has a certain pattern and it goes out to infinity. And if you get very far away, where you're so far away that the two charges look like one charge, then now the combined field looks like the charge of one charge. Like that, the field is a thing that can exist in space, even if no forces are there. So really, the term force field is not a term that I want you to even think about or use anymore. That's a Saturday morning cartoon term, which is like not really science. There is a force, and then there's a field. And those are two different things, as we've been describing, based on Oh, wait a minute. What am I saying? I'm just confusing you. We didn't do any charge today. Oh my God. Sorry. I'm thinking of the other class. Sorry. What I just said was next semester in terms of, but I will explain the difference between a force and a field. Sorry, but let me go back and do that example again. Based on the discussion we were having today. See this thing right here? This is a mass. Right now, there's a force on this mass, right? It's a force of gravity and it's acting down, as we've been talking about. Now, at that point where this object exists, there's a force. But if I take this object away, at that point, there's no force anymore. But is there a field there? Yeah, there's a gravitational field that's associated with it. Now, I know you've been thinking about gravitational field as a force field. It's not. It's an acceleration field. You can only have a force at a point if an object is there to be forced upon. If there's no object there, there's no force at that point. But there can be a field, and you can think of the force, once you put a particle there, you can think of the force on that particle from two different perspectives. You can think of it as a force coming from another particle nearby, like the Earth, or you can think of the force as coming from a field that is in this area. Now, yes, that field is created by that Earth, but still, you can define the force on a particle at a particular point in space solely by the field in that area that's created by some other object without thinking about that other object. Or you can think of the force on that object on that object as a force associated with an object that's nearby. There's two different perspectives that you can talk about. That's all I'll say about that right now. And we'll talk about that a little bit later as we move forward. But yeah. So sorry, back issues. It's a lot of talking. I think it's hopefully it's interesting for you. At least you have some sort of background now for some of these things you probably heard about: dark energy, dark matter, field, force. Well, I mentioned the idea of a field because a field has two things associated with it. It has a force, in the case like gravitational field around a heavenly body. That field is there, and if you put an object near that heavenly body, that object will apply a force on that object. And again, as I said, you can think about the force that's coming from the object or coming from the field created, the field around that object created by that object. So a field has a force, but a field also has energy associated with it. At least certain type of, conservative fields have energy associated with it. So what I believe is that possibly, one alternative explanation of these two, arguably the biggest problems in physics now, cutting edge in quantum mechanics, are trying to find dark matter and explain dark energy. I happen to believe that there's one possibility that most people, mainstream people aren't really considering, is that these two things are actually connected. That dark matter, first of all, and I will not, it's being recorded, so maybe I shouldn't say it, but I'm going to say it anyway. I actually don't believe that dark matter exists. I don't think that's where the force is coming from. I don't think it exists. I think that there is a force. Basically, I think that there's a field in the universe that we have not identified, or at least we might see it, but maybe thinking about it, or at least see it, but thinking about it in a different way. I think there's a field that we've not identified, basically. And I think that because a field has energy and force, this dark matter and this dark energy is the force and the field, the force and the energy associated with this field. And so those two things, they're connected. And the key to finding them, to understanding them, is to try to figure out the form and of the field and where the field is coming from. That's what I think. Yeah. So, just a bit of background about where we are in terms of forces, which is what we're introducing in this chapter, and what we know about forces in the universe, and what we at this point, how we are describing those forces. So 4 fundamental forces: strong and weak in the nuclear forces that basically hold matter together. And then we have these gravitational force and electromagnetic. Basically, all these forces are associated with atoms, because the atoms are the smallest building blocks of the universe. So yeah. And grand unification is the attempt, which quantum mechanics is trying, cutting edge physics is trying to unify all the forces. 3 of them we've unified. Gravity is a big holdout, and that's where we are. Now you might ask yourselves, well, you say those are the fundamental forces, but we've already been talking about some other forces that are not listed there, like drag, like friction, and there's other forces, All other forces other than these fundamental forces can be grouped together in something called contact forces, which basically are combinations of these 4 forces, essentially. At least these 3. Contact forces are essentially atomic forces, right? It's like in order to have a frictional force, 2 surfaces must be in contact. Drag force is actually a contact force as well. Contact with what, you might ask? Because when a space shuttle comes back into the atmosphere, what's it contacting with? Well, it's making contact with the atmosphere, right? The molecules in the air, those things it's physical matter. They are made up of atoms. And they might seem like, not so intrusive when you're moving very slowly, but when you move very fast, right, those things can have, effect on the object. That's why you have to have heat panels on the shuttle, because it gets very hot. I mean, you don't even have to go that fast, really. You can go like ride your bicycle and just stick your hand out, and you can feel the wind on your hand. So clearly, like, drag forces, as we'll see, are associated with velocity, the magnitude of velocity, and it doesn't take long before those drag forces at certain velocities can start to impact the objects that are moving, within that medium, and begin to affect the object. So contact forces, are things like friction and drag, and there's viscous forces, viscosity. All these forces basically, are manifestations of combinations of these forces. And you can think about it, like when 2 objects, you take your hands, you rub them together, right? What happens? Your hands warm up. But we macroscopically, in this class, we think of the surface of our hands, right? It's a flat surface. But if we could blow the surface up, what we would see on one level of order of magnitude is the surface of our hand would look like a mountain range that we look at, and we look at like the Hollywood Mountains or something, right? Like, it's going to be very uneven and jagged. And we just can't see that because the order of magnitude is so small. But if we blow it up, then, our hands are going to look very jaggedy. If we continue blowing it up, what we're going to see is just combinations of atoms moving around, vibrating right on the surface, not even stationary. So when we put, the reason I can't take my hand and push it through my other hand is because when we come together, those atoms, those atomic forces, basically are resisting the ability of one object to move into the other. So ultimately, it's resistance of all these different electromagnetic, the nuclear, the strong, weak nuclear forces are resisting even gravitational force, technically, because protons and neutrons have mass. So on a level, you still have gravitational forces inside, the atom, inside the, particles. It's just that gravity actually, and I didn't say that, but of all these forces, gravity is the weakest, like much weaker. In fact, we're going to show how much weaker gravity is from electromagnetic. We can show that next semester, but it's on the order of like 10,000 times. And of course, the weak and strong nuclear forces, I don't know how much stronger they are than electromagnetic, but much, much stronger. So gravity doesn't even compare in magnitude. It's so ironic like that. Because when we look around in our physical universe and in space, it seems like gravity is the big deal. Like gravity is stronger than everything, but it's by far the weakest force. But somehow, as you get larger bodies, it seems to be the thing that controls everything. And it does kind of, but it's the weakest. And when you get smaller, you see that really it's these other forces, like when you're looking at atoms or looking at matter, it's almost like gravity isn't even there. It's so weak compared to the electromagnetic and the strong and the nuclear. So when we get down to, what makes you not able to walk through a wall, basically is the fact that these forces are resisting the particles of one object to interact with the particles of another object. Yeah. So contact forces are associated with these. This is what we call the forces macroscopically, but ultimately they're just manifestations of the weak, the strong, and the electromagnetic forces within matter. And finally, 4 basic properties of all force. 4 basic properties. Force is a vector quantity. Forces always occur in pairs. That's because of the third law. We'll come back to that and talk about that more specifically when we deal with the third law specifically. Our force says always, without exception, occur in pairs. Forces cause acceleration. Or force causes acceleration. That's the second law. And deformation occurs because of force, external force. So an object can be deformed by forces can deform objects. All right. Yeah. Yeah. Cool. Okay. So that's kind of the formal introduction to forces. I like to put that discussion of the first law in there as part of the introduction, as opposed to kind of doing the introduction. Maybe I should, because it just seems more contextualized than leaving it out and doing this other thing, talking about, yeah. Yeah. So anyway, that kind of introduces the 4 forces and the forces and So now let's go back to working. I've already worked two problems. The one with the one with a sitting mass and the one with a mass moving at a constant speed. So that's the illustration of the first law. Superposition principle is a principle that states that when we, it's a principle we'll be coming back to over and over again, all the way from Physics 39. So you want to grasp it now. It leads to something called vector analysis, and it's the idea that whenever basically you can add forces. So I've implied it here with the first law, like I had an object on the ground and I had two forces on them, a force up and a force down. Now, those forces were acting along the same coordinate direction. So I could very easily add them. One is in the negative direction of the other. But it's not so obvious how to, or that you can add forces when they're not along the same coordinate direction. For example, second, a little setup here. Work on some more problems. But it helps to have a visual demonstration. Yeah. So let's say that I have two chords, and I'm going to hang an object by those two chords in a mass. So that those two chords would be applying a tension force on the object. And I want to make one visually very different. Size. And finally, I will need a 35 minutes. Let me get a little mask here. I think this will do. Okay, wonderful. So we've got a statics problem here, where you have two objects, one object that's held by two cords. So those cords represent forces that are on the object. And of course, the third force on the object is the force due to gravity. Now, if I were to sketch this problem, you can clearly see that there's a fundamental difference in this problem and the ones I did before. And that fundamental difference is that none of the forces are acting in the same direction. So you can't just add them up in the way that I added those forces before. The force, in order to add a force, they have to be along, you have to, because you know, force is a vector quantity. So it's not just the magnitude that you have to consider, it's also the direction. And you cannot add a force unless it's along, it doesn't have to be in the same direction, but it has to be along the same coordinate direction, meaning it'd be parallel or anti-parallel. But either way, if it is at some angle, other angle, then you can't add them. So then what you have to do is find the components of those forces along different angles that are along the same coordinate direction. So here, if I were to diagram this, assuming that I'm placing the center of mass right there at the object, then a free body diagram of this guy would look something like this, where I have gravity straight down, mg, along what we would say would be the positive y direction, or negative y direction. So mg is there. But then I've got the object has two other angles, at angles relative to the horizontal. So, over here, I've got a force, and we'll kind of make that smaller angle relative to the horizontal, maybe something like that. So that's T1, you could say. And this guy's a little bit steeper, so maybe we could do something like T2 on that guy, like that, exaggerated. So all three of these forces are acting on the thing. Now, superposition says that the net force on this particle is the vector sum of all individual forces on the particle. In fact, I've got a much more verbose definition, but let's just use that as a superposition. Let's just state that as a superposition. Superposition says that the net force on a particle is equal to the vector sum of all individual forces acting on that particle. So that allows us to be able to analyze basically apply something that we call vector analysis to the problem. So the principle of superposition is the thing that allows us to do that. The net force on a particle is equal to the vector sum. In fact, maybe I should do it like this. So the vector sum all individual forces on the object. And all individual forces would be represented as a net. So F sub i's. So I guess mathematically what I should write is that F net on a particle is equal to the summation phi equals 1 to n of all the F sub i's on the particle. So this is the mathematical version of this qualitative definition, description, superposition principle. And put emphasis on vector sum because vector sum implies that we have to find the components and stuff. Now, I have already defined what components are. I think we described that, didn't we, the other day when we were doing kinematics. We were talking about components. I had to flashlight all that. I think that was this semester. Semesters are running together. We did that, right? Yeah. We already talked, I defined components already by doing the arrow on the shadow. I'm not confusing that with the previous class. That had to be this class. Because we did, I usually do that in kinematics. So somebody tell me. We've already described, I've defined components already, right? The projection of onto a lower dimension and all that. Is anyone there? Seriously? So no one's in class. I don't know, I think it's on my notes. Yeah, okay, thank you. Thank you, Cheryl. Yeah. All right, so again, remember all that stuff. So over here, so that's what justifies it. So we have to find the components. So over here, and what you'll see is that the components do lie along the same coordinate directions, namely the y and the x. Right? We have y and x. Now, mg is already along the coordinate directions. I'm not going to have to worry about that, but the T1 and the T2, I will. So I'm going to have to define an angle. In this case, I could measure the angle. I'm just going to guess. I don't know what it is. But, that looks like maybe something like 30 degrees. So I'll just call that theta 1. And this is something I want you to finish for homework or for a class. It's not to turn in, but for your class homework next. So, you set it up for you, let you do it. Now, yeah. Now let's say that this mass, I don't know, that mass is probably worth like 15 grams. So in that case, let's say that, if F is worth, if M is, for this problem, if M is equal to 15.0 grams, find T1 and T2. Find what they are in terms of, given quantities. And let's assume we would have to know the angles. So assuming that theta 1 is equal to 30 degrees and theta 2 is equal, I don't know what that looks like. Say 75 degrees. Pretty steep. Now, Newton's first law applies to this. Why? Because it's not moving. Well, not only that it's not moving, it has no acceleration really. Clearly, the acceleration in the y direction is 0 of that particle. Acceleration in the x direction is 0. So I know that Newton's first law applies. But I have to think about it in coordinate direction, that the net force in the y direction equals 0, and the net force in the x direction equals 0. But right now, I only know one force that's in the y direction. The other forces are not. So I have to find, give me the projections of those other two forces in the x and y directions. So I can map it out just kind of qualitatively. Again, this is not a graph, it's really just a kind of a drawing, that this component T1x is, that component, and this component over here is T1y. Probably should have done different colors so we can, I will do different colors so you can see it better. I meant to do that and I forgot to. So T1y is here. So T1y. And this guy will make a different color. It's easier to see it. Don't pay attention. So now here I've got a T2y and a T1y, or T2x, excuse me. Now, for all practical purposes, I can forget about T2 and T1. Like, I'm not going to redraw the free body, but if I redraw the free body, I've got 5 vectors. I've got one mg, then T1x, T1y, T2x, T2y. Now, applying the first law to both coordinate directions is going to give me what I call a system of equations, linearly independent equations that we can solve simultaneously. And in physics, that's ultimately what we're doing every time. In the problems I've done yesterday and then, last week and then to this morning, when we got down to step 6, I was kind of, we basically have that. Like, you apply those equations of motion, you apply the equations that apply to the problem in step 5, that gives you a set of equations, and those equations you're going to solve simultaneously. You generally always need the same number of equations as a motion, some of the equations as unknowns. And in this case, given that I know the angles and I know the mass, I have 2 unknowns. So in order to solve a system of equations, you're going to always need the same number of unknowns, same number of equations as you have unknowns. So since I have 2 unknowns, I need 2 independent equations. The components of Newton's first law in the x and y direction give me those 2 equations that I can apply to the problem, and then that gives me a system of equations that I then solve simultaneously to solve for the unknowns. That's a process in general. In this case, we're using vector analysis in order to process of the mathematical tool of vector analysis to do that, to institute and find our unknown. Now, again, I'm kind of going a little bit quickly as what I normally do because I think I talked a whole lot in comment. But basically, you have alternate interior angles here. So like this angle here is the same as that angle there. So that's how I got it. I would measure that angle and realize that's the same as my theta 1, right? And measure this angle because bisecting parallel lines bisected by a third, that angle there is the same as this angle here, which I'm calling theta 2. Okay? And so again, the vectors are pointing along these lines and whatever. So it's a description of what we have here. Classic statics problem. Statics because not only do we have 0, acceleration is equal to 0, but the velocity is also equal to 0 of all the components. Statics. Okay. Cool. All right, so let's apply that. Now, I can also break this down into 4 different parts, vector analysis, that is. Let's break it down real quickly. Kind of give you, so vector analysis, it's got 4 basic parts, 4 or 5, it depends on who you talk to. So, one is kind of what I've done here, is you have to first determine the magnitudes and angles of the vectors in question. Like I've kind of, because we're kind of working backwards. Like a lot of times we want to find other things like, well, yeah, let's just say this. Just in this case, you analyze basically what vectors are applied and what directions those vectors are in. So I guess determine angles. Well, determine magnitude and direction of applied vectors, or identify applied vectors, let's say that. In this case, so identify magnitude and direction of applied vectors, applied forces. Then we find components of those forces. In fact, when I say applied forces, let me call those the F sub i's. So magnitude and direction of applied F sub i's. Then find the components of the F sub i's. And when I say F sub i's, that's just the counter. So determine the components of the F sub i's. Then we have to add all those F sub i's together and find the resultant, the components of the resultant vector. Because the resultant vector is ultimately thing we want to determine. So then determine components of resultant of the F sub r, which is the resultant vector. And then find the magnitude and direction of F sub r. And then determine mag and direction angles of F sub r. And so we essentially are using the components, part 3, the components of F sub r to do part 4. So that's kind of a very short-handed way of going through that, of talking about breaking up vector analysis into 4 parts, which is the way that I think about it. And I know you may not really fully understand what's the difference in the F sub i's and the F sub r right now, but I want to give an outline, and then I'll point those out as we go through. But right now, the F sub i's that I'm talking about are the applied forces. And in this case, that's Ti and T2. Now, we're identifying what those are and what their directions. Now, sometimes we will know those things and we're just finding the total resultant of them. In this case, we are basically gonna not quite do this. We're gonna, because we don't know what the F sub i's are, but still we could do that process to work backwards to see what they are. So it's a little bit kind of convoluted, but it's because we're doing vector analysis for the first time and not using it actually in the way that we will be using it, but rather here I'm set up a problem that actually defines what it is. So once we get through this, we'll be kind of using it in a slightly different way in subsequent problems. So this outline is more how we will be using it from this point on, as opposed to what I'm describing here, although it's still useful to think of it in those terms, the 4 different parts, even for this problem. Well, let's just get to it. Let's go ahead and set up the stuff so you can do a little work before you leave here. You'll need to use the restrooms and take a quick break. But basically, I showed you how to do this for simple problems, for the one-dimensional problems. Now, here, we're going to do this, doing the same thing. but we have to, so we're kind of like at jumping right on to step 2 here, because we have to figure out basically the components of the f sub I, in this case, T1x, T2x, T1y, and T2y. And so, where do I want to do that? Start to use all the board. So, we could just write them down, right? Because we know our definitions of geometry. We reviewed that. So, like T1x T1x is equal to T1 times the cosine of theta 1. T2y, so T1y is equal to T1 times the T1 times the sine of theta 1. You number these equations. So 1, 2, 3, 4. T2x is equal to T2 times the cosine of theta 2. And T2y is equal to T2 times the sine of theta 2. Taken directly from my geometry stuff. So that's geometry. Now we're going to apply that, put that into Newton's laws. Right? And so, let's do that here. So, in the x direction, the net force in the x direction is going to be equal to, now we know that it equals 0, right? So again, right side, motion side, left side, dynamic or force side. So what are the forces I have in the x direction? Well, I have T1x in the positive x direction and T2x in the negative x direction. So T1x minus T2x equals 0. Putting in what those are in terms of T1 and and theta 1, I have that T1 cosine theta 1 minus T2 sine, no, what? Yeah, T2 cosine theta 2 equals 0. Now, as I told you before, these are 2 unknowns here, right? So 2 unknowns, I know that I'm underdetermined. I at least need another equation before I can even try to start solving the mathematics. Because here I would just get T1 in terms of T2, and that doesn't really help me. So I go to the Newton's first law for the y direction and apply that. So net force in the y direction also equals 0. And what forces do I have in the y direction? Well, I have that equation is going to be T2y plus T1y minus mg equals 0. Now, putting in my geometry equations into 11, I have T2 sine theta 2 plus T1 sine theta 1 minus mg equals 0. Now, again, a word about the signs, not the trig functions, but the plus or minus. Here, this is minus because these 2 forces are in opposite directions. Here, the T2y and the T1y are positive because they're in the same direction, and I'm calling that the positive direction. The mg has to have an opposite sign from those 2, which in this case, I'm calling the negative direction. And so now you can see that equation 12 has two unknowns as well, the same two unknowns. So that means that at this point, the physics is done. I'm what's called equally determined. When I have the same number of unknowns as equations, then I don't have to apply any physics anymore. I can just do my math and get my unknowns I'm looking for. If I am underdetermined, then I had either missed some physical concepts that apply that I need to go back and apply, or I've missed some equations associated with this physical concepts that I found, because sometimes they have more than one equation, physics concepts, or both. I've missed concepts and equations in all regards. But in this case, I'm equally determined and I'm done with my physics. So now from this point on, it's just mathematical manipulation. Now, I want to get away from the high school version of solving problems where as soon as you get a number, you take that number and start putting it back in the stuff. What I want is analytical solutions for both these unknowns. So basically, we're going to solve these two things together. But we could solve when you get a number and then take that number and put back into either one of these. But what I want to do is get a solution, take the solution, put it back in to get another analytical solution for the second unknown. And the reason I do physics like that is because you begin to see symmetries. Remember, that's a theme of the course, symmetries as you work problems. And it tells you things that you wouldn't normally see if you were just looking at the numbers. But thus far, any questions about what I've done? Oh gosh. Okay, well, there's a couple routes I can go. I think the way I'm gonna do one of these, and I want you to finish it, and then also in the end for homework or before tomorrow, check to make sure you can do it, and then put in the numbers that I gave. And I won't remember the numbers, so you have to remember for me the numbers I just made up, because I'm just making this up off the cuff. I don't have this particular problem in my notes. I think the easiest thing that I see is I'm gonna take mg over on the other side, then I'm gonna solve equation 9 for like T1, for example, and then plug that into the other thing and then do out the algebra. I think that's what I'm gonna do. Yeah. So if I did that, let me go ahead and put mg over here. So here, so T2 sine theta 2 plus T1 sine theta 1 equals mg, okay? From this guy, take the T cosine, T2 cosine theta over, and then dividing by cosine theta 1, it's gonna give me that, and I could solve for either T1 or T2, doesn't matter. I do it for T1. So T1 equals, it doesn't matter, whatever. So T1 equals T2, and it'll be cosine theta 2 divided by cosine of theta 1. And this is from 9. Now I'm going to take 14 and substitute into 13. Right? 14 into here for T1. Running out of space. So I'm gonna erase this over here. Yeah, I guess I don't need this anymore now that I've shown you this. Four minutes, I can do this in 4 minutes. So sticking that guy in, So 15. So we've got the T2 sine theta, that's there. 32. The T1 is this guy, so T1 I'll put in brackets. T1 is going to be T2 cosine theta 2 divided by cosine theta 1, and then times the sine theta 1 that's still there. And then the mg is on the other side. Okay, sine theta 1 over cosine theta 1 is tangent theta. So I have T2 sine theta 2 plus T2 cosine theta 2, the numerator, times the denominator, sine cosine is tangent, theta 2 equals mg. Now I can factor out the T2 and then divide through by what's left. So I'll do that in one step just for time. So T2 is equal to mg on the other side divided by sine theta 2 plus cosine theta 2 tangent theta 2. Something's wrong. This should have been tangent theta 1. Sine theta 1, cosine theta 1 is tangent theta 1, and this is tangent theta 1. So that gives me an analytical solution for that force, that tension force, in terms of all the given quantities. You just go back and put in the angles that I said, which I don't remember. But you'll remember, because that's how smart you are. So good like that. You tell me tomorrow. Now, because I've done this a long time and I know what I'm going to get, but also I can just write down the solution of the other thing. But I want you to work it out to prove it to yourself. And I can write it down. I'm showing you the value of what we call symmetry. The value of symmetry can work this out for you. It's the value of symmetry here. So here, the T1, you're going to get the angle flipped around. It's going to be equal to mg divided by sine theta 1 plus cosine theta 1 times tangent of theta 2. And that just, goes from, we'll do it a couple. You could just come back here and solve this for tangent. Basically, T2 is equal to T1 cosine theta 1 over cosine theta 2. Plug that back in and work it out, and you get that. So why don't you go ahead and work out, so finish it, put in the numbers, see what the numbers are. So here's the solutions, get the answers. But also go back and make sure you can work through it by working this by yourself and maybe setting it up again, just to practice. This is a standard problem. Standard physics problem is going to be right in, some version of it will be right in all the chapters that you're going to be doing. And that shows you the power of the first law. The first law, all you need to work statics problems is the Newton's first law. Okay. That's the 4:30, right on the button. So how do you feel? This was a good day, I think. We got a lot done.